So in the interest of time, while Jelena is setting up here, I will introduce Jelena. Jelena is, let me get this right here, the Jensen Huang professor in the School of Engineering, and she's also a professor, of course, in the electrical engineering department. But one other point I should mention is that she is also a professor by courtesy of applied physics. And Jelena is going to talk to you today about, I think, some of her photonics work. She is also the leader on the campus of a major new initiative in quantum mechanical science and engineering, our engineering professor. And she epitomizes something that we've been proud of for many, many decades in electrical engineering, which is that we seamlessly span across the boundary back and forward between science and engineering. And I think that's a real strength of what we do. And if you're going to do that, you have to be able to hold your head up both as an engineer on its own and as a scientist on its own. And Jelena can do both of those things. She's a fellow of the IEEE as well as being a fellow of the APS. I'll just say one other thing about Jelena. I've admired her work for many years. She's been here since 2003, and I've been very pleased to have her as a colleague. And I think in some of the view graphs she's going to show you this afternoon, you're going to look at these things and you're going to say, what? That can't possibly work. How does that work? I love these view graphs. These pictures of things that she has made. And I used to occasionally show these as examples in my talks myself, because they're a little bit related to some very different things that I do. I had to stop doing that, because when I put these things up on the screen, all people wanted to talk about was Jelena's devices, and for professional survival, I had to stop showing the view graphs. So with that introduction, I'll pass you over to Jelena Vučković.
Yeah, thank you. Well, I mean, while we're waiting for the computer to get connected, I should tell an interesting story. What I'll be talking about today is not quantum, that's half of my group's work, but I will mostly talk about our work on optimization in photonics, and that's something that I'm sure I wouldn't be doing if I were at any other place. It's completely influenced by being surrounded by this great group of people and faculty at Stanford. And these are the structures that you saw on the front slide that I'll be showing you. And since I'm the last talk between the reception, I'll try to keep this very entertaining and keep you all awake. But let me first acknowledge my group and my colleague, without whom this would not be possible. So this is my team as of last month, and about half of my group are physicists, half are electrical engineers. And as I was telling today to Joe Goodman, usually physicists who come to my group, they want to do something very applied. And electrical engineers who come to work with me, they want to do something very fundamental. And it's been like that for many years. And some of the things that you'll see today are actually led by physicists in my group working together with electrical engineers. And of course, I collaborate with a lot of people. And even for what I'll be talking about today, I collaborated with quite a few people from Stanford. You see a long list here, including David, who just introduced me, and Stephen Boyd. And I'd like to tell you a funny story, actually how a lot of this started. And it started when I interviewed for my job at Stanford in 2002. One of the people who I met was Stephen. I came to his office and he told me, I see you have this paper on optimizing resonators. And I'm like, yeah, I'm very proud of it. And after about 5 minutes, it turned out that what I was doing was not an optimization. But anyway, I got a job and we started collaborating, and we still collaborate and even jointly advise students. So thank you, Stephen, for spearheading this research. I work on photonics. You know that photonics has a lot of applications. People are talking about using photonics in data centers for optical interconnects to reduce energy consumption. In fact, David Miller is the world-leading authority on that. Then there was a mention of optical neural networks today, quite a few startups working in that area. LiDAR, of course, many startups working on that as well. Quantum technologies, quantum computing, although some of the leading platforms for quantum computing are based on superconducting qubits, you still need optics to connect them into quantum internet or connect different modules into something that works better. Augmented reality systems, virtual reality systems, Gordon was talking about it, and quite a lot of effort there as well, and imaging systems. And for all of this, you need to use optics and photonics. And in many cases, you cannot really solve this with bulk optics, free space optics. You actually have to do integrated photonic solutions because your augmented reality glasses need to be also very small and compact and pretty so that people would like to wear them around. So the question is, can photonics really go through the same revolution that electronics went through in 20th century, where from the computers that occupy the whole buildings in the mid-20th century, we right now have way more powerful machines inside of our cell phones? So that's the question that has been driving our work and that we've been trying to answer. But in order to answer this, let's first look into how photonics, kind of state-of-the-art photonics, has been for the past 10, 15 years. So it turns out that photonics is pretty large, right? People generally make components that are tens or hundreds of microns in size. These are some of the examples of the typical devices used for filtering in optics. Then they're very sensitive to fabrication and temperature errors. So you make this device, and then you have to also make some other circuit that tunes this device, which also consumes a lot of energy. So that makes everything very complicated and power hungry. And then they're designed by manual tuning of few parameters. You take something that you know from grad school that you learned in your optics class, and then you tweak few parameters until you make it better. But a lot of these designs actually were adopted from microwave engineering, where people could only solve problems by hand. And there is really, as you'll see in a moment, no reason why we would be actually doing things the same way as we did 50, 60 years ago. There are also limited functionalities. There are also not a lot of devices, not enough devices for a lot of things that we would like to build today. And efficiency is a very big problem. Even in commercial systems, you lose about 50% of the power when you're coupling light from a fiber to your chip. And that was actually quite surprising to me because I thought that problem, at least in photonics, has been solved. But it turns out that it hasn't been solved efficiently. So the question that we wanted to address was whether you could do things in a much better way. So can you make things smaller so that they're kind of more comparable to electronic sizes? Of course, you cannot beat diffraction limit if you want things to be efficient, but at least you can make the things smaller. Can you make them robust to fabrication errors and temperature variations so that you don't need these very complicated tuning elements in addition to all of your photonics? Can you build new functionalities? And something that John Hennessy mentioned today, can you actually design hardware in an easy way comparable to the way you write software so that nanophotonics expertise or photonics expertise is not really even required in the design process? Can a circuit designer design photonics? And we think the answer to these questions is yes. And I'll tell you how we can do that. And we've been working on this for a long time, again, 17 years from the day I joined Stanford. But about 6 years ago, we made a breakthrough when we could finally design devices in 3 dimensions. And of course, for manipulating light, you have to worry about all 3 spatial dimensions. If you do things in 2 dimensions, it's not enough. It doesn't work as well when you make it and you have a 3rd dimension as well. And it also turns out that the optimal solutions don't look like anything you've seen before if you took photonics classes or you learned things in grad school. They look like this. And when people see these pictures, and these are actual color filters, wavelength filters, they think, oh, this must be really hard to make because it looks like Swiss cheese. It looks like nothing we've ever seen. Well, it turns out that fabrication constraints and robustness to errors and robustness to temperature and environment are incorporated into the design. So when we make these things, they all work the same, despite the fact that the fabrication process is not the same. So they work much, much better. And this is a growing field of what we call inverse design in photonics, and there is a lot of effort in this area in our department, including David Miller, Jonathan Fan, Shanghui Fan, Stephen Boyd, of course, who is an inspiration behind a lot of this work. And it's, of course, very active outside of the Stanford as well, and it's becoming kind of the mainstream of how you approach photonics today. So what are we doing? Well, it turns out, as David, quoting David from a few years ago from one of his papers, that every linear optical device is a mode converter, right? So if you would like to design any device in photonics, you basically just need to know what field you have at the input, what you would like to have at the output, and then you have to find out some distribution of the electric constant of material in the black box in between that would do that particular mapping between the input and the output. So how do you do that? Let's say you have a piece of silicon. I would like to do conversion from the first order mode to the second order mode. They're drawn here. They have one lobe or two lobes. It doesn't matter. You don't need to know optics to understand this. So the question is, how do you do this? Traditionally, you would do this by so-called adiabatic mode conversion. So you take a waveguide and slowly expand, and you need 300 micrometers of waveguide to do mode conversion. So we were wondering whether we could do this in 2.5 by 1.5 micron of space of silicon with greater than 90% efficiency, right? If you do it with a 2% efficiency, it's not good enough, right? You need to do it with a high efficiency. So now, when you start solving this problem, you don't know in advance whether there is a solution to this problem. In fact, this is one of the things that we would like to address now in collaboration with Steven. But generally, we start from some footprint, and we say, well, let's see if there is a solution. So you may say, OK, I have silicon here, and I'll just try all the possible combinations of silicon and air pixels, and one of them may work, right? And that's, in principle, OK. But even if you take a very big pixel of 100 nanometers, which is very large for optics and would cause a lot of scattering, and this tiny device, you will have 10 to the power of 112 combinations. And running 10 to the 112 simulations, electromagnetic simulations in 3 dimensions, is impossible. Right? You will not be able to solve this in your lifetime unless you're extremely lucky. So you can't really do it that way. So how do you solve the problem otherwise? Well, you have to do optimization, meaning you still have to search through that enormous parameter space, but you can't do blindfolded search. You actually have to follow some kind of physics-guided trajectory. So then you do optimization, you define figure of merit, and you apply a variety of optimization techniques, and here is how your optimization trajectory looks like. This is the first stage of optimization where you allow your permittivity, refractive index, or the electric constant, to vary continuously, and then you initialize the second stage. And on the right, you see electromagnetic field. You see this is doing mode conversion, but on the left, you have something that you cannot make. And then you binarize that, and you continue optimization, and then you obtain mode converter. And indeed, you can do greater than 90% efficiency inside of this tiny footprint. And there is actually, in addition to this, another 6 devices that do it with equally high efficiency, which tells you that we're doing photonics in an extremely suboptimal way. There are so many better solutions than the ones that we normally use in everyday life. And to solve this, you still have to run through 400 steps of optimization, run 2 electromagnetic simulations in each step, like thousands of electromagnetic simulations for one optimization. So we couldn't really do this with commercial electromagnetic solvers. We had to develop our own electromagnetic solvers, which run on gaming GPUs, speed up the optimization part. And right now, full optimization of a 3-dimensional device of this size takes about an hour on gaming GPUs. And we think that we can improve it by probably a factor of 10. So you don't have to wait forever to solve one problem. You have a solution in less than an hour, and you can actually change things and design other things in plenty of time. And that's, in general, the amount of time that you would need to run one single electromagnetic simulation of this device if you have the design using commercial electromagnetic solvers. So we're quite excited about this. And keep in mind, these are not supercomputers. These are gaming GPUs, which, of course, my students are very excited about because they can use it for other purpose once they finish their work. So you design devices, you take the layouts, and then you just use them to define your devices. These are actual devices made in silicon. These are just wavelength splitters. You need filters, wavelength splitters for communications or for pretty much any of the optical circuits that you need to make. So the actual fabricated devices are on the left in silicon, and on the right, you see experimental results measurements for these devices. And what is important to say is they perform exactly the way we designed them. And when we measure many of them on the chip, they all perform the same. And that never happens in optics. Remember, I told you about tuners. So you take one device and then the another one, and if you want the other one to be the same as the first one, then you have to tweak temperature or something to line them up. All of these line up without doing anything. And they were made by my students in the nanofabrication facility, and of course, our fabrication is not perfect, but even industrial fabrication is not perfect. But they all work the same because fabrication constraints are incorporated into the design process. So we design them to all work the same. And if you're interested in playing with this, we released open source software on GitHub. We call it SPINSB. Actually, that's an acronym for Stanford Photonics Inverse Design Software. But it's also homage to what other part of my group is doing in quantum optics, which are spin-photon interfaces. But actually, we are quite excited. There is a very large community of people out there, thousands of people already using our software and designing things. So that's how we started. We designed things, we made them in the fab at Stanford. They worked. We were quite excited. We published papers in Nature, right? That's great, for students. But then we figured out that in order for this to become practical, we have to show that we can make things in a foundry, right? Because using electron beam lithography by students at a university will not work. So we spent several years working with foundries and showing that what we design can be made in a foundry. And we were quite optimistic, but of course, it took a lot of time to translate process to foundries. And right now, after working with several major foundries, we know that this is possible. So this is from recent work with AIM Photonics. What we do is we generate these layouts that you see on the left. We just send these GDS files to them. They make masks. They do design rule checks. They make masks. They expose them, send us devices back. We measure them. And they all perform according to the specs. And this is one example of a spatial mode splitter and converter, which kind of splits two modes and converts the other one mode to first order mode at the output. You would use this to capture both polarizations from the input fiber to save half of the power that you are normally not using unless you have these mode converters on the chip. And here is the simulated behavior or design behavior. This is how they're supposed to work. And this is the experimental result, and this is measured result for many of them, right? No tweaking, nothing. We just receive them from the foundry, we measure all of them, and they all work great. So that's quite exciting, right? And that's the practical part, which we emphasize right now, because you can actually design devices to really be practical, and you don't have to spend hours and hours finding for the one that works, because all of them work. And also compared to the devices that we designed and made and previously fabricated at Stanford, like this color splitter, we send the same designs to foundry, we receive them back, we measure them, and compared to the theoretical behavior, they also all work great. So you don't really need to use very slow, low throughput fabrication capabilities of Stanford nanofabrication facility or other nanofabrication facilities. You can just send your files to a foundry, you receive your chips back, and you can make them. And it's not that this is important for commercializing these devices or doing high throughput fabrication. It's also great for students not to spend many, many hours fabricating structures. They can actually do interesting science, they can do designs, and they don't have to spend many, many hours tweaking etchers or E-beam writers. Okay? So we're doing a lot of interesting things. I also mentioned that this is opening opportunities to design new functionalities. And I'll just show you 3 at the end. These are really new functionalities that are offered by this approach that we couldn't solve otherwise. One problem that we've been looking into is the issue of isolation. For those of you familiar with integrated photonics, you know that optical isolators are kind of holy grail of integrated photonics. How do you isolate reflected signals so that they don't go back to the laser? And there are a lot of beautiful solutions, but they're not really practical. On-chip solutions, of course, you can buy isolators off-chip, but how do you integrate them on-chip is not trivial. So we're collaborating with the team of Andrea Liu, who is at the City University of New York. He demonstrated a proof of concept using microwave platform, but it was very difficult to transfer that to optical platform because we didn't really have the right functionalities. But we knew what transfer functions we needed. We knew that we needed nonlinearity, so we just let the optimization software design things for us, and these are elements that the optimization software designed. By hand, we wouldn't be able to do this, but then we designed it, we measured things, and indeed, it actually isolates, blocks backward pulses. It just propagates forward pulses. So these are kind of the most technical pictures in my talk, but anyway, you can see that in the yellow slots, backward pulses are blocked and only forward pulses are propagating. And then we also use this in a ranging measurement where reflected pulses were just routed to the detector, and that was used to measure distance from the target, which you actually need to do in a LiDAR. And of course, there are off-chip switches and routers that you can use in a LiDAR, but in this way, you can integrate all of that in few microns of the chip. So your LiDAR doesn't have to be a toaster sitting on your beautiful car. You can actually have a LiDAR that will eventually be half of an inch on a chip. And I should also emphasize that this particular work, for example, involves not only my group, it involves also a collaboration with Shanghui Fan and Armin Arbabian from Stanford, and also we did some experiments in David Miller's group. So a lot of people worked on this in a very collaborative manner, which illustrates how things are done in our department. Another kind of crazy idea is shrinking accelerator. You all know about SLAC, but the question was, do you really need so many miles of accelerator to accelerate electrons? And Bob Bayer at Stanford has been leading this for many years, and the idea was to replace radio waves with laser fields, with optical fields, and shrink everything, shrink all the stages of accelerator onto the chip. But we didn't really know exactly how to do it. Bob's team did an experiment 5 years ago where they showed that they could do acceleration, kind of proof of concept acceleration, but it was not enough to scale it up. And the goal was to go to relativistic electrons within a single wafer, right? Can you go to mega electron volts, accelerate electron to mega electron volt energies within 4 inches of a silicon wafer? And in order to get there, we had to design stages of accelerator, and we didn't know how to do that by hand. And then we actually decided to do the inverse design, and here is how the stage of an accelerator would look like. So you see in the middle the waveguide, vacuum waveguide for electrons. You see crazy-looking structures that are designed so that the field, optical field coupled from the laser, is always in phase with the electron. It just accelerates it, it never decelerates it. And we have experimental results. We have, when we turn the laser on, the electrons that are coupled from a converted scanning electron microscope that has 80 kilo electron volt energy are accelerated, and acceleration gradient is greater than 40 mega electron volts per meter. So this is only 30 microns, right? So we showed that we have enough acceleration, detectable acceleration within 30 microns of silicon. But of course, we can pack a lot of stages of this accelerator within a 4-inch wafer. And we think that with what we have right now, we should be able to replace SLAC with a single silicon wafer. And that's not Large Hadron Collider, right? We won't be able to do high-energy physics experiments on a chip, but you can actually generate X-rays on a chip. You can do a lot of material science. You can do a lot of medicine without requiring miles of an accelerator. And we're quite excited about going there. And finally, quantum, which is a very significant effort in my group. You've heard about quantum advantage, quantum supremacy experiments from Google published last week. There is a lot going on in industry, in quantum computing, but also in academia. It's not just quantum computing, it's also quantum networking, quantum communication, quantum sensing. This is something that we've been doing in our group since also I joined Stanford. Right now, we're trying to combine new materials and also optimization techniques in order to build the systems, build interfaces for quantum computers so that we can connect modules into something more powerful. But also, we're trying to build quantum simulators that do not rely on neutral trap atoms in a chamber, that instead rely on just impurities inside of semiconductors. The same impurities that give very nice color to diamond, but kind of arranged in a controlled manner. And here, I will not really talk about details of those experiments. I'll just say that we are here, it's even more important to have very highly efficient structures and new functionalities because all of your information is in a single particle of light, right? And you don't want to lose them in 90% of the time. So we're using inverse design to design structures, and we're relying on new fabrication techniques. And of course, here we have to do it in our nanofabrication facility because there is no foundry yet for diamond. But I'm sure if someone demonstrates quantum computer based on this, there will be a foundry for diamond, and we don't have to make it. But these are structures that we etch, first design using our inverse design, and then we etch it in a block of diamond. And they have these color centers. You can't see them. They're not with very high density as the ones that you would have in jewelry, but they're the ones, they're qubits of your quantum computer. And we do the same in silicon carbide. Huang spoke about silicon carbide as a power electronics material. I'm actually very excited about silicon carbide as a photonics material and quantum material. It also hosts very interesting color centers. It's a power electronics material. It's used in sanding paper. It's also used in some inexpensive jewelry, but it's a very interesting material for photonics. And we believe that it would have a very important role in quantum sensors, quantum networks, and quantum simulators. And there as well, we're combining new fabrication techniques with the design techniques in order to make these new building blocks. And you see crazy looking structures with color centers, and these are in fact, these are structures for quantum networks that we recently demonstrated. So with that, I'd like to conclude my talk and just say, I spoke about photonics, and photonics, really the future of photonics and all of the quantum technologies is really in merging very powerful optimization techniques and design techniques with the new science that people have discovered. And there is a lot of effort on quantum computing, for example, and quantum sensing, but it's really difficult to start from the building blocks that all have to be individually tweaked and controlled, and they're very difficult to make and make very precisely and in a controllable manner and combine them into something functional that works. So in order to enable scaling inspired by what has already happened in classical computing, we really need to make blocks that are more robust to errors, more robust to environmental changes, and then scale them up into something that is much larger and much more powerful. So that's what we're doing in classical photonics in a variety of materials, and also what we're doing in quantum. And with that, I'd like to finish and acknowledge again my group and our collaborators in funding. And thank you very much for your attention.